Okay, let's jump right in and tackle one of the most profound, kind of mind-bending mysteries of the quantum world. Why a confined particle can literally never sit perfectly still. We're drawing directly from Chapter 5 of our source text today, and while we're going to use the classic infinite square well to get our bearings, our real destination, the big payoff, is Section 4, where we explore what happens when those rigid boundaries actually start to break down.
But first, picture this. It's 1993, and physicists at IBM's Almaden Research Center managed to pull off something absolutely incredible. They actually imaged the electron density inside a microscopic ring of 48 iron atoms, and the result? It wasn't just some smooth, featureless puddle of electrical charge. It was a series of sharp, concentric rings, a distinct standing wave pattern. This is huge because it takes this highly abstract idea and proves it in a perfectly tangible way. Simply confining an electron physically and mathematically forces it to take on structure. The boundaries themselves are what dictate the particle's behavior. Now, to wrap our heads around how those concentric rings actually form, we really have to talk about quantization. You've probably heard the term, but it basically means restricting a physical quantity, like energy, to a discrete set of allowed values. But here's the absolute most important part of that concept. It arises directly from confinement and boundary conditions. So quantization isn't just some magic assumption or a random quantum rule. It's a completely natural mathematical result of trapping waves inside a container.
To really see the mechanics of how this works, let's build a theoretical sandbox to play in, the infinite square well. By looking at this rigid, impenetrable trap, we can build the foundation we need to eventually conquer the more realistic, finite boundaries of Section 4. So imagine a quantum particle trapped between perfect, unbreakable walls that demand the wave function drops to exactly zero at the edges. By starting with this extreme constraint, we can see exactly how simply locking a particle in a box forces a continuous range of energies to abruptly collapse into a very strict ladder of allowed states.
And the math behind that collapse is just beautiful. If you calculate the energy levels for an electron in a 1 nanometer well, they aren't just random numbers. They scale by exactly n squared. This means those first few states jump in incredibly strict ratios, 1 to 4 to 9 to 16. It's like a cosmic staircase. Now, if you widen that well tenfold, or say swap the electron for a much heavier proton, it definitely lowers the overall energy scale. But that fundamental n-squared shape of the staircase, that remains completely universal.
When you picture that base state, the ground state, it's essentially just one big central peak, right? It has no interior nodes, meaning it never crosses the zero axis inside the well. But the moment you jump up to the first excited state, suddenly there's a node right dead in the middle, creating two peaks. You can literally see the Fourier logic working under the hood here. Every extra interior node forces a shorter wavelength. A shorter wavelength means higher momentum, and naturally, that means higher energy.
But honestly, this begs a really fascinating question. Why can't the ground state just sit still? Why can't it have an energy of exactly zero? Classically, if you put a marble in a box and take away all its kinetic energy, it just sits dead, perfectly still on the floor, doing nothing. So why is the absolute lowest allowed energy for a quantum particle strictly greater than zero? Think about a regular classical guitar string for a second. You can mute it, right? You can stretch it perfectly flat so it has zero energy and zero frequency. But a quantum particle is a totally different beast. It must always possess a minimum non-trivial mode with strictly positive energy. You quickly realize that the quantum wave isn't a physical string at all. It's a wave of probability amplitude, and it absolutely refuses to sit flat. The real culprit behind this refusal is what we can call the Heisenberg uncertainty trap. Think about it step by step. A trapped particle has a maximum position spread equal to the width of the box. If the particle's energy were exactly zero, its kinetic energy and its momentum would also have to be perfectly zero. That would mean the momentum spread is exactly zero. But if you multiply a finite position spread by a zero momentum spread, you get zero. And that instantly violates Heisenberg's uncertainty principle bound. Simply because the particle is confined by the box, it's mathematically forbidden from having zero energy. So that inescapable, strict limitation forces the existence of a zero-point energy. For a 1 nanometer electron well, this absolute minimum energy sits at about 6.0 times 10 to the negative 20 joules. Now that number is phenomenally small. It lies roughly 20 orders of magnitude below anything we could casually measure in our daily lives. And that right there is exactly why this restless energy is completely invisible in our macroscopic world, yet entirely runs the show at the quantum foundation.
Okay, so we know the particle always has this baseline energy, but how does it actually behave in these pure states? Well, a pure energy eigenstate is what we call stationary. Now wait, that doesn't mean the wave function itself is completely frozen in time. The wave function's real and imaginary parts are actually spinning in the complex plane, constantly oscillating 90 degrees out of phase like the hands of a clock. But crucially, its probability density, the actual part we would interact with, remains perfectly still. It's like the unmoving shadow of that spinning clock hand on the floor.
But things get totally wild when we start mixing states together. If you take a pure stationary state, the probability density just sits there, completely unchanged over time. But the moment you create a superposition by combining states of different energies, that stationary privilege is completely gone. The probability literally sloshes back and forth across the well, like water in a bathtub.
And when I say it sloshes, I mean it sloshes insanely fast. In a 1 nanometer well, the superposition starts shifting at 0 femtoseconds. By just 1.83 femtoseconds, the bulk of the probability has swung entirely to the other side. And by 3.66 femtoseconds, one full beat period is complete. Because the relative phases of these distinct energy states are drifting apart over time, they create a rapidly moving interference pattern that swings back and forth in blindingly fast femtoseconds.
Let's tie all of this together. The underlying Fourier math dictates that the total energy of the system remains completely conserved. Basically, your energy measurements just reflect the static initial weights of the different states you mix together. But position measurements? They reveal a completely dynamic reality, the interference of those shifting Fourier phases. The internal probabilities are constantly dancing to the beat of drifting phases, even while the overall total energy stays strictly locked in place.
Now, everything we've talked about so far relies on this idea of perfectly impenetrable walls. It's the cleanest, simplest way to see why confinement forces quantization and zero-point energy. But this brings us right to the core of Section 4, and our final, most provocative mystery. How does a particle behave when those boundaries aren't perfectly rigid? What happens when this restless, inescapable zero-point energy is actually allowed to leak into the classically forbidden zones? Well, you've just arrived at the threshold of quantum tunneling, and it is the perfect place for us to pause and let you ponder just how wonderfully weird the quantum world really gets.